everyone, welcome back again to our class. Good morning. So how are you? Before we start, let's wait for the others to come in for about 5 minutes, okay? I think everyone is here, so let's start our class with a prayer. Anyone in the class who can lead our prayer? Okay, thank you. Amen. Very good. So good morning once again, class. By the way, I am Marianeña Rama, your student teacher from Central Mindanao University. So for today, we'll be learning about volumes of solids of revolution. Now, you are tasked to find the volume of a solid of revolution obtained from a simple function y equal to f of x between given limits as x equal to a and x equal to b. So let's find out the volume of solids of revolution. Now you are tasked again to find the volume of a solid of revolution using the disk method and the washer method. So we'll be learning about methods here in finding the volume. Okay, first I have here a question. So why we need to study solids of revolution? Okay, as you all know, you are enrolled in a STEM strand, so you'll need to study this one to prepare your knowledge about integration or about the future course you want to be. Okay? The solids of revolution are used commonly in engineering and manufacturing. Some examples are axles, funnels, pills, bottles, and pistons. So as you can see here, how can we get the volume of these things? Okay? So now we will be learning about getting the volume of these things using the formula. So we'll be learning about two methods or two formulas here. See this video for further discussion if you want to on your own. Okay? So imagine that the part of the curve between the ordinates x equal to a and x equal to b is rotated about the x-axis through 360 degree. So imagine that this curved line here as y equal to f of x is rotated around the x-axis through 360 degree. So what will be the resulting figure then? So if we have here a curve as y equal to f of x, will be rotated around the x-axis here. So what would be the resulting figure? Okay, hence we'll have this figure. It will be rotated around the x-axis and this is the resulting figure. Okay, the curve would then map out the surface of a solid as it rotated. So such solids are called solids of revolution. Now, how can we find the volume of the solid here? Okay, how can we find? So let's start for the formula. So schematically, we have first the disk method. So from your known pre-calculus formula, you have the volume of disk. We have volume equal to pi f of x squared times width. Our W here stands for width. And now it has then representative element. We have delta V or delta volume equal to pi f of x sub 1 squared delta x. Now, in integration, we will have to stick in this formula. So we have here volume equal to pi integral from a to b f of x squared dx. Okay? So that this method, or as we have known, we have the coordinate plane, right? We have the horizontal axis of revolution and the vertical axis of revolution. Now, if our solid here is rotated around the x-axis, it will be called, or it will then map out to with respect to x, right? If we have horizontal axis of revolution, then we'll have this formula. We have volume equal to pi integral from a to b, or its given limit here, which is a and b, and multiplied by f of x squared dx. So dx, if the rotation of the volume is around the x-axis. Now for the vertical axis of revolution, or the y-axis, or with respect to y, we will have this formula. Volume equal to pi integral from c to d multiplied by g of y squared dy. Okay? So using the formula of this method, so we have pi integral from a to b times f of x squared dx or dy. So using that formula, let us derive for the volume of a cone. So suppose that we have a cone of base radius r here and vertical height h. We can imagine the cone being formed by rotating a straight line through the origin by an angle 360 degree about the x-axis. Now, this curve here is rotated around the x-axis, right? So we have here 2 points. The first point here is the coordinate 0 and 0, right? And the second point here, we have h and r, right? So using the slope formula, we have m equal to y sub 2 minus y sub 1 minus x sub 2 minus x sub 1. So our y sub 2 here is, we have the point r given in this figure, right? So we have r equal minus 0 over h minus 0, because our x sub 2 here is equal to our value of h, right? So now we'll have r over h as our slope. Now we'll have, then using the point slope formula, we'll find out its slope formula. So we have here our point slope formula. We have y minus y sub 1 equal to m times x minus x sub 1. So now we'll have y equal to 0, as our y sub 1 here is equal to 0, and then equal to r over h, our slope, times x minus 0, as our x sub 1 here is also 0. So now we'll have y minus r, y equal to rx over h. So any questions regarding this one? None? Thank you. So let's proceed. So the limit of integration are from x equal to 0 to x equal to h. As you can see, if the volume is rotated around the x-axis, so our curve here is at point 0 and h. Therefore, it is our limit of integration. So we will have then the formula for the disk method, and we'll have to derive for the formula in finding the volume of a cone. So we have here formula equal to pi integral from a to b times f of x squared dx. So substitute the given value. Our limit of integration here is from 0 to h. Then we have pi. Our f of x here is equal to rx over h squared dx. So we have here with approaches to x, because the given volume is rotated around the x-axis. Now we'll have here volume equal to integral from 0 to h pi times r squared times x squared over h squared dx. So as you can see here, our squared here is distributed to r and x, and with also with h, right? Now we'll have then volume equal to pi rx squared times x cubed over 3h squared, integral or evaluated from 0 to h. Now we'll have this, and the final answer is the formula for the volume of a cone, right? So we have here volume equal to pi r squared h equal to 3. I hope everybody got correct. Anyone in the class who have questions regarding this one? None? Okay, let's proceed. So using the disk method, we have here volume equal to limit from delta x approaches to 0, summation times summation from a to b delta v. Then we will be using integration in finding the volume. So we'll have integral from a to b pi y squared dx. So if y is given as a function of x, the volume of the solid obtained by rotating the portion of the curve between x equal to a and x equal to b about the x-axis. Okay, so this would be our disk method. So don't get confused if we have here y, or we have here y squared or fx squared, because y squared or y is totally equal to f of x. So don't get confused by this, because y is definitely equal to f of x. Okay, using again the formula, we will derive for the volume of a sphere. So as we will rotate this curve between x equal to negative r and x equal to r about the x-axis through 360 degree to form a sphere. So if we will have to graph -1 or negative from -1 to 1, we will have then formed a curve, right, or a sphere, half sphere. So it will be easy if we will graph, then we'll have its figure. So this is the resulting graph as y equal to square root of r squared minus x squared. Okay, so we have here the 2D figure and the 3D figure for your understanding. Now, x squared plus y squared is equal to r squared. And so we will have y squared minus r squared minus x squared. Therefore, using the formula as volume equal to pi integral from a to b f of x squared dx, then our limit of integration here is from -r to r, or -1 to 1. Pi, our f of x here is r squared minus x squared dx, because as you can see, it is rotated around the x-axis. Now, using the formula or using the integration, we'll have pi times r squared x minus x cubed over 3, evaluated from -r to 3 to r, because we'll have if you ask why it is 3 here, x cubed from x squared, it is because we integrate the given value, right? As you remember how to integrate, so that is why x cubed over 3. Next, we'll have then evaluated from -r to r. Then we have the given formula for the volume of a sphere. We have 4 pi r cubed over 3. So any questions and clarifications? Now, in a sheet of paper, answer this one. It is mark your activity. So we have here the question. It is using the disk or a washer method. So for the disk, we have this question. The curve y equal to x squared minus 1 is rotated about the x-axis through 360 degree. So we will find then the volume of the solid generated when the area contained between the curve and the x-axis is rotated about the x-axis by 360 degree. Okay, so we'll find this out. So let's check. As we calculate the volume as follows, we have here our formula, right? So for the formula of our disk, we have volume equal to pi integral from a to b times f of x squared dx. Now we have here the integration is, the limit of integration here is from -1 to 1. So we have integral from -1 to 1 times pi times x squared minus 1 squared dx. So as you can see, our f of x here, or our y here, is equal to x squared minus 1. And then we will have to substitute the given value for our f of x or our y, and then it is equal to x squared minus 1 squared dx, as explained or as discussed in the problem or given value. So we have here then the pi integral from -1 to 1, and then simplify x squared minus 1 squared. It is equal to x to the fourth minus 2x squared plus 1 dx. Now we'll have then, using integration, we'll have pi times x to the fifth over 5 minus 2x cubed over 3 plus x. The integral of our 1 here is equal to x, and that is evaluated from -1 to 1. Now we'll have to evaluate both limit. Then we'll have the final answer. The final answer, 16 pi over 50. I hope you get it right, class. Anyone, if you have questions, just feel free to ask. You can comment in the chat box if you have questions, and you can raise your hand to notify. Okay. Now, for the washer method, it is different from the disk method. As you can see, our disk method does not include a hole. So for our washer method, it is included with a hole. So how can we find the volume of a solid if they have or it has hole? So now suppose the generating region R is bounded by two functions, y equal to f of x on the top and y equal to g of x on the bottom. So as you can see here, we have two radius here. So this time when you revolve or around an axis, the slices is perpendicular to that axis will look like washers. Okay. The difference between the disk and washer is that our washer method here, it has hole, and our disk method does not have hole. Okay. And then a washer is like a disk but with a center hole cut out. The formula for the volume of a washer requires both an inner radius or r sub 1 and outer radius or r sub 2. Now, for example, the area bounded by the curve y equal to x cubed, the y-axis and the lines y equal to 1 and y equal to 8 is rotated through 360 degrees about the y-axis. So find the volume of revolution generated. So we have here the figure. If we'll have to to graph y equal to x cubed, so using a graphing calculator or a Desmos calculator, so we have this resulting figure of the function y equal to x cubed. So find the volume of revolution generated. So we have here the 2D function and the 3D function or the figure. Now for the solution, we have here y equal to x cubed. So if we will have to simplify x cubed, we have x equal to y to the power of 1/3, right? So as you can remember, your exponential function, okay? So how can we find its volume? So now the axis of revolution is on the y-axis, so we'll have to use with respect to y. So we have here volume equal to r integral from c to d times g of y squared dy. Okay, so our integration here, or our limit of integration, is from 1 to 8. Now we'll have to substitute the given value x. We have y to the power of 1/3 squared dy. Okay, integrate and evaluate. We have the final answer, v equal to 93 over 5 pi. Now, if you have questions, class, you just feel free to ask me, and your worksheet and the remaining topic or the remaining slides of this topic, I will be sending it to you. So that's all for today, and if you have questions again, you have free will to ask me. Okay, so that's all for today. I hope you got learning for today's discussion, and we'll see you next time. Bye, class.